If noticed, now that we all know the results of the award ceremony, today's day of our winners, and it's a great pleasure and honor to start with one of the winners from last night's ceremony, Alberto Verjovsky. So I've known him since 1989, since Trieste, and through the years he has been helpful very much in the promoting the idea of IMSA and the organization of the collaboration with Mexico. So it's a great pleasure to introduce a friend of mine from more than 30 years, a great mathematician and humanitarian, Alberto Verjovsky.
Thank you very much for the introduction and for your comments. So this talk is you see the title. So another manifold, so that's called small dimension 1.3, and it's motivated by this material contained in this paper, which was published in this paper last year, and it was a volume, this is including a volume dedicated to the 80th anniversary of Dennis Sullivan. So this is highly motivated by ideas of Dennis Sullivan, and you can see most of the material in this paper. So let me tell you what I'm going to talk about the material and the topic of the talk. So given an integer, topological k-dimensional solenoidal manifold, the solenoidal lamination, simply k-dimensional solenoid, is a complete metric space which is locally modeled on the top of a Euclidean open disk of dimension k, and non-empty compact or disconnected and tricycle perfect set. If I all the names that characterize the type if the space locally is closed with an open subset with closed fields, then you have a boundary is, and you can also talk of another manifold with boundary model of that. When k equals to 1, sometimes they are called polynomials, that's the original name, and they originate in topology by the work of the structure of the Hurder damping independently of the periodic solenoids, which are from the fundamental examples in topology and examples of many ideas. So we will see this space. I'm sure you all see this. The Hurder torque. Inside this Hurder torque, you embed a solid torque which is quite long and has thick, and you wrap it in time, and inside the yellow, you put the green, and inside the green, you put another color which has 2 times around the green, and it's 4 times smaller, and you take a net equal to 5, just like the following picture, vertical Wikipedia. Here you see at the very end, you see if you take a disk, if you take a disk here, transversal to the, you see that the first toroid, the green toroid, meets in 2 disks. Inside these 2 disks, there are 4 disks, etc. If you come to a transverse to this intersection, you will see a cantor set, and actually you will be the mapping tool, you are in, the mapping from cantor set to itself. And it's a very beautiful thing that it's like what could be a one-dimensional manifold, but it's the metaphor that Dennis called that this is an infused manifold. So you take your glasses, you say, oh, that's a filter, that's trapped around 2, what do you put for concentration in the utility, a filter that wraps 4 times, and but actually this is something that looks like cantor, and I will see later that this is only particularly for a group, logical group, no locally connected group, and I will, but these topics appear in various guises in all mathematics. So solids appear naturally as the contrarian dual of discrete locally compact Hauser-Billiard groups. So contrarian duality attached with locally compact Billiard group, another group called contrarian dual, and discrete Billiard group, they called compact, and vice versa, the contrarian duality. So all the thing is most is you take the rational in the discrete topology. You are squatting or conjugate dual. Well, let's start with the integers included in the rational, and the conjugate dual in the circle. If you take the whole group of the rational, then you get what is a beautiful object called the adelic solenoid. And it's a beautiful object that contains a lot of arithmetic. In fact, as a basis, our first step is famous pieces like those days. And it's a beautiful object. They play Cantor-groups, well, of course, zero-dimensional solenoidal manifold against Cantor set. But Cantor set have the first of a topologically. You know, it's something that when they ask you in the first years of the course, you prove that the Cantor set is homogeneous, and you will start constructing the Cantor, use the Cantor set and more usually prove it. But if they tell you it's a complex that we do, then you know how to continue to mathematical translation and so this is that. So a complex dimensional manifold is a kind of set. They play a very important role in our modern dynamics. Some of the invariant sets obtained by the Taylor theory, and also the Taylor Cantor set. And I think last but not least is one of the great contributions for the last part of 10 years ago is our prefixal spaces, a collection by Peter Schultz, and prefixal spaces are it's a paradigm of the use of solids. In fact, the prototype of a prefixal space is a reality solid. Well, this talk I want to record the definition for the other manifolds with more precisely and establish some of their problems. Some of the most important examples of complex dimensional polynomial manifolds are obtained as inverse limits of an infinite power of regular covariance of complex dimensional manifolds. With infinite or singularly finite fundamental. You have a manifold that has the property that its fundamental groups are singularly finite, and that implies that you can take a tower, increasing tower of finite covers, and then take zero freely. You take one point, the covers over A, you have two points, you have a sector, and you can easily prove that this gives you something that fibers from the manifold with fibers Cantor set. Now, if the covers have to be regular, then of course now you have group structure, the group of vector formation, and what you have is a beautiful object is a Cantor bundle over Cantor-group bundle, principal bundle over the manifold. And just because this model is collected, we should worry. Treat as if what a group happens to be totally is correct, it doesn't matter. And for this beautiful characterization before many, we shall obtain a infinite towers of finite covers of a band. This theorem of McCord implies that the solenoid, which is obtained that such a tower is topologically homogeneous. Topologically homogeneous means you can go from any point to any other, like and create or point to a homogeneous, abstractly the group of homogeneous. Of course, because the principal bundle or the regular cover is a principal bundle, you can move the point around 5 by translation, act by this translation, but then along the middle you can always move, and it's important to see that these are homogeneous. What is very surprising is the opposite. That is the theorem of Clark and Hurder, and it states that a complex solenoidal manifold which is also homogeneous is McCord solid, namely it's obtained as an infinite power of regular covers.
So why does the group need to be residually defined?
What?
Why does the group need to be residually defined? You will get
Yeah. So you have an infinite tower.
but you will get some good law. You will get
Yeah, no, but I mean, one of the fundamental thing is that all homogeneous, all expected here have an infinite tower, have a level group of the single finite.
Yeah, because they're linear.
Yeah. And something that is very important history that I will go over is the fact that this idea may code commensurability. So two manifolds, N1 and 2 are called commensurable. If there is a third manifold that's called invertible. And so you will see that this is called commensurable. You can ask whether the current speed with the manifold. But anyhow, this works for residually fine. In my work. Because of this reason, because the fundamental group is the final condition. How do you go? How do you go? Yeah. Okay. I was going, that's all my mistake. I made a mistake, so sorry. It's okay now. Now I'm going on now. Okay. Hey, very good. So, el de abajo para bajar. Sí, pero. Sorry for Spanish, with the universal language. You can see my own. Okay, so this is the theorem say that the reciprocal is that solenoidal manifold that is topologically homogeneous is actually a thing as a infinite tower of regular colors. And in fact, the Cantor-group is the provided condition of fundamental group, which is a very important thing if you want a algebraic fundamental group. And for this reason, it is a talk, I will talk of G for modern group. So now, say that. All the question of belief, all simply connected compact solvers like the manifold with any fundamental group have infinite residually final fundamental group. Then a fifth division of manifold we have power. And as I told you, there is something I will speak about and then mention something interesting. There's a famous theorem which is taught a question by McCord. McCord says every dimensional hyperbolic manifold is finitely covered by one that follows from the first. So it's obtained by mapping total of surface with a unit map of mapping total with a several of each. And therefore, and you will see you can start with power for each manifold and compare them not information. So it's okay. Well, all these solenoidal manifold can actually behave as manifold, and you will see. It's exactly like a manifold is well. Let me say this. If you give the fancy definition of covering, non-revetement, as a principal bond group with value and discrete group, it's a model application. It's a fiber you replace with split fiber with totally connected fiber. So you may think of it as an orientation of covering. And you can see the animated structure, and you want the idea of this block is treat them as they were manifolds and see how far you can go. Okay? And so you can find all the notions of the manifold. Actually, if you take the power of all finite columns, you can actually you have a final set for the water available. And in fact, with a given tower, an inversely in the case if you take a tower is associated to a geometric set, And if I coverings are directed by inclusion, by theory of coverings, corresponding two groups on their inclusion, and you can always actually take regular coverings, not distinguished coverings, because the set of regular coverings or finally the set of coverings, which is well, if I want to treat solenoidal manifold as manifold, many questions pertaining to manifold arise. For example, can I triangulate on the manifold? Can I give a differential structure for the differential manifold? Are solenoids which are homeomorphic but not isomorphic? Are etc. etc. Of course, then this was a paper in honor of David Sullivan. We have to remove the code to the I failed that explanation between so let me okay, you will need a manifold with there are also homomorphic of efficient for some reason resolved by Cipriano Moretti says that for any n greater equal than 5, actually greater equal than 4, you can obtain a topological manifold that is not homomorphic but efficient content. You can only triangulate it in standard set. Before the way example of manifold can only triangulate it from the forest. By Chile and the Kilo, etc. Down and there is a stronger for the manifold can only I know homomorphic. So we will have a ratio with progress and anything. And we also talk a little bit about that. I will talk a little bit about the theory of covering spaces, the Alberto response to problems. We should be responsible because these things are totally connected. You have the caveat of covering, no? These things exist, but they are not unique. They are, but and if we reduce to the particular case of foliated one-dimensional for another manifold, then a theorem of Solenoidal work says that every such solenoidal manifold actually a mapping source. It's not difficult to prove, but it's for the mapping source that has been selected for a non-dimensional manifold. It's not said by taking a homomorphism from the Cantor state and constructing mapping source. And also another theory is that any one-dimensional solenoidal manifold actually bound at the dimensional lamination. It's topologically. And this is a theorem because it's a theorem of David Sullivan. And so this is what it means. Given a oriented solenoid is the boundary of the dimensional. So you see, McCord solenoid dimension 1 means that there are columns of the circle. And the circle has a beautiful property that a covering is, or it's a covering, it's covering mapped by total homomorphic to the group structure one. Any covering of the one equals to the A is V is a complex number of modulus 1. So all these towers of the circle are actually a billion groups. And as I say, all the dimensional connected solenoid. I hope the two is connected. Connected solenoid one-dimensional manifold is actually a concerning dual or subgroup of the graph. And so, by duality concerning duality, if you take the whole rational, that covers all the beyond invariancy of the choice. So then I will consider also the dimensional lamination. And one idea that has been solved that I will see is you take the surface continuous to any surface, any oriental or compact surface, continuous greater equal than covers the surface continuous to the surface by the space. So again, you take the surface continuous to and take the power of both finite covers. You get a beautiful object. It's called the universe has the wall navigation invented by David Sullivan, and it's beautiful because now you can take, for instance, all the basic on the top of the and we implement it with this. And you can argue that every hyperbolic metric is that way. Can you construct category theory, and there is one can construct category theory, and in this case, it's an dimensional scalar manifold, and it's really interesting. And I will also describe a little bit that picture of theoretic category space is contractible, and there's a canonical map. It's a final form of the species of category space that called category space.
So what is the category space?
This parameter the laminated composite structure context on the you see a theory that I want to say here that we have fully there to prove is the most of the given theory for McCord hyperbolic dimension theory. The two sources are the modern actually I mentioned. But this one is a modular, a little bit in dimension, it's a perfect modular space is a complex space of minus 3. So this is in dimension. And this codifies all category space that we call the universal category space. A beautiful idea to codify in one dimension all category space of every genus and every time. It's a very beautiful object. If you are treating this dimensional lamination as if it was a real problem. As you will see, you can talk about laminated triangle position, laminated matrix, everything you do with manifold, you do manifold, or you do in this mechanical characteristic. This idea. You can find the Riemann matrix, you can find bond, you can find the category boot, bond, or bond, you can move anything on. Maybe you can find this bond. Why not? And you can thought about it. You can find anything you do with a manifold, you can move it for another manifold. If you take your glasses and you expect a manifold wrapping itself in time, you just want to move everything you do with the manifold to another level. But it's a new question you have. You can identify the opposite structures of the lamination. Okay, you may ask, and I think you can we deform hyperbolic lamination? And the answer is yes. Do you have a rich flow along the list? You have in dimension 2. In dimension 3, the Feynman theory will work because you have to be direct. But anyhow, I'm going too fast. Anyhow, this is so let's start more clearly. So this is the definition of solenoidal manifold. As you can see, it divides a chart that are for open set. You feel the space time at that scale, and you have the coordinate changes, the usual except that you require the coordinate changes out of this form. This means that it shuffles the flat. The kind of open set is a ball in the field of space, you should any time space. And if you want to change the coordinate, you always do. The always see these are like foliated charts, and therefore this chart automatically you can make the ask that they are smooth, they are complex, they are reality, they are you have a whole thing. And so you can speak of all everything, all the notions like TP exposure, reality exposure, everything. And you can even speak of an orientation, and also in this case you can speak of fundamental class, depending on the volume form that I will speak. Well, this is the definition of charts for forces, etc. The transversal space of Cantor says. And for the smooth dimension, what I told you, one can define all the notions of integration topology and geometry along with these. For instance, what they call laminated group functions, laminated Riemann matrix, laminated curvature, the rough theory, cost theory, everything you can do. In particular, you have the following definition, the old definition. Differentiable functions are continuous functions, you are only as transverse continuity by all the leaves to infinity. So the leaves are manifold. As the next force or estimate the leaves, we start at definition. So you can, as I told you, all volumes they say times in volume, one particular ratio for everything. And but is there subtleties in the notion of differentiability. And of course, you define what is smooth map between the require the more into this category of the only a continuous map by differential between. So and with your morphics, the same notion, exactly. Okay, this is a topologically homogeneous, is what I told you. One important thing of solenoidal manifolds, final form with one of the Cantor-group, McCord solenoid, is that they have the problem that have a unique passivity problem. They behave just like orbitals. If I respond, if I see what the whole chapter of that, fiber modules with totally connected fiber. I have a beautiful property of this. So that means that you have a solenoidal manifold, which is McCord, maybe a Cantor bond over surface. Then you can see your holonomy, take a form, take a path, and you need this path, give you a map of the Cantor-group, and you have a general representation of the fundamental group of the base manifold with McCord. I mean, the angular bottom is the base manifold with McCord, and you have a representation of the fundamental group of the base manifold with the group of homomorphisms in the Cantor. And this is the notion here, holonomy. Okay, so these are the theorems important. McCord says a compact solenoidal manifold is okay at the I told you already, I read it again. Obtaining by infinite tower regular fluids of the beam of increasing beam of a compact connected manifold element. Then they are topological homogeneous. It's easy because the principal one. This is the issue of McCord solenoid, but the opposite is very interesting. I don't see that. It's simply a compact connected topological homogeneous of another manifold. It's on a non-trivial theorem. Then sigma is actually the same as a infinite tower of always. In particular, something very interesting that is minimal. All these are the example of minimal mechanical physics. Like the solenoidal lamination, the infinite tower of always the top of the all the these are actually, if you have the body all of these are isolated in this. So the McCord solenoid, the lead is the universal solenoid of man. And so this is a beautiful theorem. They are using the reciprocal. Now, as I told you, you take the power, the direct set of all couplings, but there's a particular uncountable directed set for things chaining as a combined update. So if you have a tower which is complicated like a tree, with covered down, you might take a chain or always a chain, a combined update of couplings. And therefore all our couplings are of this form. We start with a base manifold M. So we start with that. You can always assume the use that. Okay, here, yeah. So you can always assume that you have a tower. You can say that the direct is actually a chain. And so this is not an observation which is important here. If you take this following, the base manifold A, and you take a sequence of following, And you take little bit of that. Then one idea is what happens if I crop the first n term. And then you start following not with n0, but with nk. And then the result, or the obvious result, is that the e takes the a. So this is called the crop map. And that's why this theory codifies for me, of mind. You can crop the thing and get the same thing. Here the monodromy that I was telling you, I don't speak anymore. Have a representation of the Cantor-group into almost the Cantor set. And so you can think of this manifold according to the following way. Take the universal covering of the main manifold, multiply it for final completion, a Cantor-group, and add by this transformation to this in the obvious way. So our first x of the universal color K in the Cantor set, act in x by this transformation and in the Cantor set by translation. And then you take a force. That means that this object, anything across the profile condition, is like the first laminated version of the universal covering. And gamma, the final condition, acts like this transformation. Okay, the following are how this solenoidal balance can be extorted. So there's a very beautiful theorem, the proton structure theorem, which states that the structure of a manifold element is the category of PL, equals linear, topological, or differential person for every if dimension of any greater equal that. So this permits you to take example. You see the first example that I take the solenoid in the green and the many different sequence. If you multiply that solenoid with one dimensional solenoid by a manifold, you have 3 examples of solenoid of higher dimension. And therefore, underneath you will be n plus r. And therefore, if I find exoticity in a manifold, exoticity means a manifold that possesses several differential structures, so a manifold that possesses several PL structures, or a manifold that can be triangulated, artificial complex, a manifold that can be combinatorial triangulated. Any example, n plus r will be also we have that property. So let me give you a more complete example. Let's use the beautiful theory of the system by the array field. So for any greater than you take a group of homogeneous spheres, theta n, for the coordinate classes of spheres of relation 7, we know that this manifold is a group, is a simply group of order 38. And what the following integral in this case, if you take n1 and n2, S7 with 2 different differential structures, n1 plus 1, then the n1, the CP covered by n1 plus r, and the other is covered by n2 plus r. And then these two manifolds, you wrap this manifold cannot be the one. And the proof, I mean, there's a proof, but proof very simple and easy. Because therefore, the one, you take a copy of n1 with far to the left, you take a copy of n2 far to the right, and by elementary topology, you do that one. Between is a covering, an edge covering, and therefore, by the table is covered, so they will bring the one. So that means if you take two exposed spheres, technical spheres that are not isomorphic, the chemicals are because isomorphic. Any one of R is isomorphic chemicals are. And therefore, this is this is the proof related elementary topology, essentially prove that they are not. And the consequence of that is that you take the solenoid of BDB multiplied by N1 and these are homeomorphic, but they are not isomorphic. You have at least 28 differential responses of this one. It's a very interesting theorem. Then therefore another manifold can be triangulated. It's the same theory. If you know the manifold creates Friedman, Michael Friedman, this is involved in zero, proves that even any quaternion matrix, symmetric matrix, N by N symmetric matrix with each zero coefficient and determinant one is actually the intersection form of a topological manifold. Now, Donato's theory says that it's differentiable here. Also well known, this possible definite standard one, etc. But EA, by Gordon theory, cannot be the intersection form of a real manifold. So what you would use one, very easy one of one progress to have a topological manifold with boundary. With intersection form CA. The boundary is homogeneous here, and a theorem by Friedman and homogeneous theory, any homogeneous here bounds are contracted the manifold to the cathode, and you have any manifold. And therefore, the same idea for multiplying this manifold by solenoids, you get manifolds that don't have. Okay, so you have this idea. Also, classical examples of theory achievement of toroids, which are no PL equivalent. For all these things, I will go into you multiply by R, the topology of T. But this is a more interesting example. I remember I asked Manuelesco, I asked him if they were simple, if you have a manifold that is not for more subdivision form. If n plus r also characterized. Actually, I think so should be consequence of treated formula. He essentially gave the proof. I finished it, but he essentially don't have to do it. I'm talking the proof. The simple triangle is a beautiful theory, result of they did that 10 years ago. There are simple triangle level application manifold for any level. And Manuelesco describes that by an invariant which he calls delta. And I prove this is this idea that multiplied by R, this invariant goes in Spanish. So you have therefore the consequence of that is this, improve. And therefore now multiply this manifold, this example of Manuelesco by the solenoid, the addition one, and you get examples of manifold. Well, you see here that the notion of differentiability is very complicated. And that is what reason that I repeat after that of manifolds that are canonical in the following way. You take a base manifold, these are differential structures of the base manifold, then have a differential property, and then have a canonical differential structure. Canonical chart, and these are the ones I consider. Well, let's try all the way. Your question is, so you have a family of covering, then you have roots, and you have the profile coefficient is a well, this is the way to that. Okay, so given total model manifold, the notion of covering, you photocopy the usual definition. But now the caveat is because the lack of recommended list of homomorphism, you don't call for homomorphism by negative, or in that the list of homomorphism by negative. But doesn't matter, either they think it's useful for many reasons. Okay. If you get a final completion of this significant thing related to the question would be, if you take a manifold with the theorem finite group, then a theory of gas science field says that the final completion, if you take a hyperbolic manifold, then there are uncountably many non-homomorphic compact systems. Right? And therefore, since there is a Galois response with an uncountable many coordinates of these solenoids. So, all solenoid manifold is the this way. Remember the Galois theory for coupling is given in the top group of the fundamental group. You have a coupling, it acts on the universal cover. The whole fundamental group acts on the elemental on the universal cover to get a manifold, and in this two groups you get a coupling back. And here you have the same theory, except now you have uncounted in many ways all this one time. And this is so the profile that Galois responding. So let you take a compact manifold, then its profile completion has uncounted in many crossover groups with coordinates are Cantor-groups. Therefore, in general, there's uncounted in many non-homomorphic, but also there are things that have over A. In the end, you have a couple of many for another manifold. And this the Galois correspondence. So what you want correspondence between solenoidal coordinates and solenoid supply. It's the same theorization. Almost will be integrated. Well, this has because the Cantor takes a group, you have invariant, you have transverse harmonization for group, you have a transverse distance. So it's just exactly like you work in a final formula. And finally, think of this for the area of photo platform, you know, except that if it happens that central part that is transverse, it's a kind of set amount of beautiful manifold, but very good. But well, here you have that. Therefore, this manifold, you take start with a manifold, the hard making, the definition, that we start with a remaining manifold. Then the power forming, and then you have a volume form on the manifold, and then you can construct a measure on it. Exactly like that. Is the measure that the heat rate is divided by the hard measure, and this is the so you have a fundamental class. That's what I mean. You have a volume form for this manifold. And this is the most canonical construction, it is suspension or representation, the analog of what Oscar spoke. You have a representation of the fundamental group into the group of homomorphisms for the Cantor set. For not a linear but very complicated dimensional perfect group. And then you will make this construction. You act on the first factor by vector formation, and on the Cantor set by the representation, and that's the way you obtain a. So you may think of my first representation. So this is the Cantor-group. That's the way the representation is given. Sometimes notation, right? So all my portfolio is expansion of a representation acting by calculation. Now I have a question that later was able to solve, and much interesting. You take a problem to GUP. You take the power of all these finite problems. I find the one by the profiling definition of the fundamental group of the problem of GUP. And then the fundamental group of the surface has all the elements A, B, C, D. And this only mathematically because we get and it was never able to describe with mass. You know, the homomorphism of the profile definition that you have this is called A type of B type of A, B, and you know the commutator of A with B is equal to the commutator of prime and prime. And what are these maps? We know, but they are not much because contain the whole information about the universal relation between problems. But that never totally go into this of that. And now there's a very beautiful paper by the groundbreaking because this motivation is having to use the residual to prove the concept. In the Congress in Madrid, we have to start with very good instead of saying, I will never forget the beginning year in my office, and told me, one will prove the comparison objective before this kind of thing. We took a seriously in the residual and the negative history. And so because Jimmy was so kind to me, that's why I was before this time. And so the residual plays a very important role, and harmonicity plays very important. So, if an example to the following, this is two manifolds, the target manifold or the source manifold, and then commodity glass. In the target manifold has a method of splitting the acceleration. There is one, and only one has one map in this commodity glass. That's the theory. I motivated all the things that I tell you. And I was wondering everything because of lamination. And that's what I did. So, really two lamination, different dimensions, compact lamination, McCord lamination. And a map of the first, the second. In the second one, I have a hyperbolic laminated machine. Then we can form the map. You have one map. So that's two. And the proof essentially similar and very cheap compete in defining energy. Because what you in something do is they minimize all the Lagrange equation for the energy. The energy function is the energy norm of the derivative with all the states. And so you have all the ingredients except what you do by the energy. And that's it. So it's not difficult, but you have to. So this is the definition of it. You see, because the solenoid has a natural demand which I call the demand ratio is this, cross hard measure on the counterpart are good. And so I have a right to see I can define this beautiful map in the energy function. You can see a section something from one. And that. So the idea is that, and then you have the Euler-Lagrange equation, it becomes complicated thing, doesn't matter. You have a disequilibrium to the tension to a tension to be identical to zero, exactly like the case of the fact. And this is the solenoid result. You have two compact McCord solenoids, different dimensions. And la medium Riemannian matrix, DLH, suppose that this effect of the target manifold, target of the manifold, has a different negative curvature, where it is put back and in the form of the and we got there's a big back in our here. And the proof follows this idea, this are but I think that this is important thing. The important thing is that the energy functional is an explicit complex function. So we look at the whole, the building. So the creating, the same manifold, the map, and the problem here, the fifth law, up to the beginning, and that is a one part. So that is why this theory is called to. So you see, I'm thinking for another manifold like they were called manifold. They are not scared of them. But for another manifold in general to be chemical state. Well, this is for the natural manifold, what I told you. Solenoid proof and any compact oriented or dimensional for another manifold is a global transversal kind of set, so they are all back and forth. Therefore, you can say that homogeneous one-dimensional manifolds are the same as conjugative graphics of homomorphism of the Cantor space. So even any homomorphism of the Cantor space is the same. Well, has to be transitive, but even to be correct, but not invalid. And then the Aluko border is an old idea by Porto. Is you have any one-dimensional unit, so you know, the manifold of not from Cantor space. Not to take cross and interval, and use the right hand to there to give homomorphism. Now, there's a theory by Anderson that the homomorphism of the Cantor is perfect. So again, my F, I give my F, can be written as form of commutative. G commutative. And now I think the representation of the first is one whole given by that. And what I have in the boundaries besides this by F of the commutator, and this is the idea of the software, so that any one-dimensional solenoidal manifold created actually have lamination and this is the boundary of this software. So it's coherent to zero. Well, here they remark that all these of it one are homomorphic. On the right of that. This is one my favorite. So now here is what if you take a foliation by given property and a compact foliation, then you give a remaining density to the angle. It induces a remaining density of the leaf, and the leaf, the universal code of the leaf, knows by the implementation theorem from A theory, I have the body, I'm a or I'm I told you. I have total negative curvature, I have zero negative curvature. Now I call by the plane, flat plane, I call by the parallels, I call by the sheet for that great stability. And the leaf knows type, conformal type. And now the origin, not problem, but more important observation, the element integrated is that if you change the matrix, the leaf remains the same conformal type. And so you can, without here, say, everything is hyperbolic in relation. The perfect state. It's an intrinsic property of the element. And therefore, we have had one directly theorem U2, meaning given a lamination by hyperbolic form. They say, as I told you, by actually indicate an array of 2 times. Can I uniformity means in a continuous manner? And I prove that it's yes, in general, but now my question is, can I do it using reciprocal? And the answer is yes, and now it's here 3 years ago, the reciprocal works perfectly well. And so the theorem is, well, people that I tell you, that leaves know their type. And the theory is, well, leaves all the blah, 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 and you can think of the triangle coefficient, you can think of any choice or you can everything you do for even total, the leaf compare alpha theory, you back do it for sort of variation. And so the theory says that, well, you have here the Beltrán equation, blah, 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 and the theory says that there's a use of thermal energy because I need to start rolling my thought, my reciprocal, already supporting that the leaves have a negative curvature, not the same concept. And then once there, I put my oven, let the reciprocal flow, and that conveys the constant curvature. So I use the theory, I use Amber's theory by energy. The theorem is that I can prove the laminated residual. And this is the technicalities is a paper about 50 pages, not very long, it's a theorem. Like visually means, and you from blue and white, is the term called residual converted to one quantum theorem. And then you have a consequence that what you know for solid systems, the equivalent if you have the one matrix, quantum matrix, etc. No? And you can describe a contract the space, which consists of all laminated categorical matrix. Okay. And as I tell you, I think I'm very close to proving the most of the geometry for three-dimensional categorical, which by this I will. We already found that no, it's such a figure I really found a mistake that I was hoping what million. So that is why I told you the Solenoidal animation, the universal category polymer. I already told you about that. These are this is the magic polymorphism that I never was able to find. It's a challenging problem. This should be one of these for a different age. Okay, so then the earlier theorem gave a highly polynomial description of binary space. As the type of outline, the thing is the same theorem holds. I told that will be. See if I can. The set of hyperbolic matrix that you can put on a Riemann-Torres hyperbolic validation is a complex element manifold on a appreciated space. The group of laminated isomorphisms act continuously and effectively, and this map is a fiber bundle, and therefore both the group of isomorphisms and the dynamic space are contracted with the fiber bundle description. And this uses this heavy proof essentially because we have the notion of energy, no, that I told you. And well, technicality, and I think that. Thank you very much.